Hello students, welcome to JCE Connect series of lectures. So we'll continue with the design problem in this particular session. So let us take one more design problem. Check the suitability of section ISMB 400 used for a laterally supported simply supported beam of span 4 meter loaded for a concentrated load of 400 kilonewton inclusive of self weight at mid span. Check for shear and design bending strength and also check for deflection. Then the load is transferred through a base plate of 200 millimeter length to the support. Okay, so this is the design problem given. A simply supported beam and a centrally concentrated load. The load is concentrated at the center like this. It is been given, and the beam, the clear span of this simply supported beam is 4 meter, and at support a bearing plates are given of width 200 millimeter, 200 mm this side, 200 mm this side. Then the effective span of the beam will become from the center to center of the support, that is 4.2 meter. Then here the clear span is given 4 meter and the support width 200 millimeter is given in a problem. Then the effective span will become 4 plus 0.2, 4.2 meter. So this one from the center to center 4.2 meter. Then the factored load, the concentrated load is given, which is acting at the mid span of the beam. Then you make it factor, that will become of 600 kilonewton. And you know the for a simply supported beam, when it is being subjecting to centrally concentrated load, the maximum bending moment will be WL by 4. And the value will be 630 kilonewton meter, WL by 4. Then once you calculated bending moment, then the next will be the maximum shear force. So again, as we know, the maximum shear force value will be W by 2 for a centrally concentrated load. Then we get a shear force as a 300 kilonewton. Then after calculating maximum bending moment and shear force, let us calculate, or let us take the properties of ISMB 400. You have to refer the steel table, or you have to refer IS 800 2007 page number 138, where you will get the properties of this ISMB 400. So since it is been mentioned in the problem, you have to take this section. So take the properties of this section, that is the depth of the section, width of the flange, then thickness of the flange, thickness of web, and also the elastic section modulus and the plastic section modulus. And these all you will get from in IS 800 2007. Even you can get from steel table as well, but except ZP value you won't get in a steel table, but you have to take it from the IS 800 2007 page number 138. And R1 and IZZ, that is the root radius of the section, that is 14 mm. For this you have to refer steel table. And also moment of inertia about major axis, that is IZZ, this also you have to take from the steel table. Okay, this IZZ is required when you do check for the deflection. Then once you noted down the properties of the section, the next is the section classification. You know how to do the section classification and all, that is epsilon value to be taken. Then the outstand of flange width, this you have to calculate for the section classification. Similarly, depth of the web, this also you have to calculate depth of the web. Then 400 minus 2 into bracket 16 plus 14, so this much you will get. Then you have to calculate the ratios of flange element as well as the web element, and you have to compare these two values with the given or the permissible values in table number 2 of IS 800 2007, so which is less than 9.4 epsilon, and this depth web ratio 38.2, which is less than 84 epsilon, which represents the section. The given section is a plastic section, and for a plastic section the beta B is 1. So after section classification, one more check you need to do, whether the buckling web buckling check is required or not. So for that you have to take the ratio of web to thickness, the ratio of web depth to thickness, which is giving less than the 67 epsilon. It means the check for web buckling is not required. Then next is a very important check, is the check for the shear capacity. For that one you have to calculate the design shear strength. The formula, as you know, Vd equal to AV into FIW divided by root 3 into gamma MO, where AV is the shear area. Then the calculate the shear area. The H is the whole, depth of whole section. Then the into thickness of web into yield stress of the web material divided by root 3 into gamma MO, and substitute all the values here. You will get the design shear strength, and this design shear strength is which is greater than the 300 kilonewton, that is actual shear force acting, hence it is safe. Then check for high shear, the low shear, whether the given section is lying in a high shear or the low shear. For that you have to take the 60% of the design shear strength, and the 60% of the design shear strength we get 280.27 kilonewton. And since 60% of the design shear strength, which is less than the actual shear force, actual shear acting, and it means this case is of high shear. Okay, so this case is of high shear. For the high shear case, since the shear is high than the actual shear, hence the design bending strength to be calculated by using formula, that is in case of high shear case, that is 60% of Vd is less than V, as per IS 800 2007 clause. If you refer clause 9.2.2 for a plastic and compact sections, and also if it is a case of high shear, the design bending strength can be calculated by using this formula: mdv equal to md minus beta into bracket md minus mft less than or equal to 1.2 JD into Fi divided by gamma MO. So that is given in clause number 9.2.2. Just I will show you 9.2.2. So here it is been given, just to refer code for a plastic or a compact section. If it is the case of high shear, the MDV that is given when the factored value of the applied shear force is high, exceeds the limit specified in 9.2.1. So 9.2.1. So I'll read again 9.2.1. See what is 9.2.1. So here 9.2 combined shear and bending. No reduction in moment capacity of the section is necessary as long as the cross section is not subjected to high shear force. That is, factored value of applied shear force is less than or equal to 60% of the shear strength of the section as given in 8.4. The moment capacity may be taken as MD C 8.2 without any reduction. But next clause what is been given here, next here in 9.2.2, when the factored value of the applied shear force is high, exceeds the limit specified, then the factored moment of the section should be less. Factored moment of the section should be less than the moment capacity of the section under higher shear force MdV calculated as given below. Okay, then this is the formula to be used to calculate the design bending strength MdV. So refer page number 70 if it is the case of high shear. Then how to calculate MD or beta or MFD, all given in this page number 70 IS 800 2007, and this is MDV value should be less than or equal to 1.2 times ZE into Fi by gamma MO. Okay. So here I calculated that one. So MDV, this is the formula I have used, and beta value to be calculated, that is beta is 2 times of V by VD minus 1 whole square. 2 into V I have calculated already, 300 divided by design shear strength, then we have got this much beta value. Then the section modulus of the flange section, that is a ZFD, you have to calculate. So this ZFD is required to calculate MFD, that is a plastic design strength of the area of cross section excluding the shear area. So means when you calculate this ZFD, that is a plastic section of the whole section minus, you have to deduct the this much area, shear area. Section modulus of the only flange section you have to take. This is the section modulus for the flange section, only flange section I need section modulus to calculate. Okay, so you have to deduct the web area. So to deduct the web area, since we are this entire section is been considered as a plastic section, so it has formed plastic hinge, then one side you will get the tensile stress and the other side you will get the compressive stress. Tensile on upper side, compressive stress, and on the lower side you will get the tensile stress. Then it will be acting the centroid of this one. So if I take this entire depth as D, then at the centroid this one is D by 2 and this is also D by 2. But this compressive stress will be acting at a distance of D by 4, at a distance of D by 4. Okay. Then you have to take area of web into, that is H into TW, that is area multiplied by H by 4. Okay. H by 4. Then substitute the values here. Okay, this formula it is. Okay, so plastic that is here given, plastic design strength of the area of cross section excluding shear area. So you have to deduct this shear area, this much you have to deduct. For that, H into TW, area multiplied by 1/4. You have to take this one. Okay, so to calculate the ZP value, H by 4. I hope you understood this one. Then ZFD you calculate, then MFD, formula is MFD is ZFD into Fy divided by gamma MO. Then you will get this much as the plastic design strength of the area of cross section excluding shear area. Then after this one, again we have got this much. Then MD to be calculated, MD is ZP into Fi by gamma MO. Then you calculated MD, this much you will get. Then MDV, finally MDV to be calculated. So substitute all the values in the above equation, you will get MDV as 260.79 kilonewton meter, but which is the actual less than actual moment acting. Hence we can say the section to be revised, and hence the section is not suitable to carry the moment because it is less than the actual. This is a the section is giving actually this much of the moment, but actual moment will be acting 630 kilonewton. Hence the section is not suitable. Else the section can be revised. But this MDV, which should be less than or equal to this much, for the when you compare with this value, the section is safe, but the actual moment will be acting this much. Hence the section can be revised. Also you have to do the check for deflection. The permissible deflection as per IS 800 2007. So this is the permissible deflection, L by 300. So this much we get. The delta max will be WLQ by 48 EI. This is for simply supported beam carrying point load at the midspan. So delta max will be this much, which is less than this one. Hence the beam is safe against the deflection. So this beam is safe against deflection, but it is not safe against moment carrying capacity. Hence the section is not suitable. So you can write a comment, hence the section is not suitable. I hope you understood this one. So this is of high shear case. We have solved low shear case in previous lectures, and this case I have taken as a high shear case. Thank you.